And she's been a wonderful, wonderful friend, and I hope you enjoy the presentation. She's now going to be starting with Merck in China, in the liquid crystal research labs, material science research labs. So it's my pleasure.
Yes. Okay. Thank you. Thank you so much. First of all, I would like to thank everyone to come to show your interest to liquid crystal display. And also, I'm very happy to visit Lens. I feel the whole environment is very promising. Future star in Pakistan, I think. I'm going to present my work, as I just said, faster response time liquid crystal. This is my advisor, Song.wmv. So first I will give an introduction about liquid crystal applications and basic theory of faster response time. And then I will talk about faster response time in three aspects. First is a special faster response time mode, dual frequency liquid crystal. And then from material side, I will talk first high birefringence liquid crystal, and such as to enable thin cell gap. And then the third, I will talk about small molecule diluter effect on the profanol negative dark ethanol liquid crystals. And finally, I will give the summary. So first, we'll give the introduction. This is liquid crystal. It was discovered in 1888 by Austrian botanist Friedrich Renizer. He observed when he this cholesterol acetate at 150 degrees, it melts to a milky liquid. And then, however, when heat up to 180 degrees, it becomes totally clear. So nowadays, then after several generations development, now the liquid crystal technology is relatively mature, and you can see it used in all kinds of products. You see the LCD TV, bigger than man, and also can be very small in projectors, people display. Also in other display applications like flexible display, e-book, or these posters, cell phone, computer. So now I just did a survey about the Chinese main LCD manufacturers in China. The main manufacturers including BOE in Beijing and Qiong in Shenzhen. You can see it has several generations manufactured. Correspondingly, the panel size increases as the generation increases. But now the most developed LCD technology is in Taiwan and Samsung in Korea. So they also invested the LCD manufacturer in China. We already know the liquid crystal display, but actually for high birefringence liquid crystal, it is also used in photonic applications. It has been used in adaptive optics. So for correcting the atmospheric aberration, and also used in optical phase array to laser beam theory. Liquid crystal-based phase array require very little power, and it is insensitive to acceleration, especially for large aperture, and also its cost drops greatly with this volume production. So with high birefringence liquid crystal material, we can realize sub-millisecond response time at infrared wavelengths. This shows to characterize liquid crystal quantitatively. We use all the parameters. So you can look at the liquid crystal molecule and the dot-like molecule, and it's aligned almost parallel with each other along a preferred direction. We define this direction as the reactor. So all the parameters follow this equation. Can you see it clearly? So this theta is the angle between the molecular long axis with the director direction. So we can understand for crystal, so all the structure, so all the parameter is 1. And for liquid, because all the molecules is very randomly, so the order parameter is 0. And for liquid crystal, the order parameter is from 0.6 to 0.8. And actually, almost every physical parameters of liquid crystal, like ferrocyanidins, viscoelastic constant, are related with depending on all the parameter. So, and all the parameter is decided by the temperature. So, we need, for each liquid crystal compound, we need to measure its phase transition. This use differential scanning calorimetry to measure its melting point, clearance point, and this is the enthalpy. So with this data, with this clearance point corresponds to the liquid crystal phase to liquid phase. This is the clearance part. So this shows a typical curve of all the parameter changes with temperature. And the birefringence is proportional to S, viscoelastic constant proportional to S squared. And this is activation energy with all the parameter. They use figure of merit as optimized to evaluate liquid crystal materials. It is birefringence square divided by viscoelastic constant. You will understand this later. Actually, this parameter means the response time. The faster response time, the larger figure of merit. And this parameter is independent of the cell gap. So it's only the it evaluates the liquid crystal properties. So this equations about use the rise time, decay time to, for example, in liquid crystal applications, we usually use a liquid crystal cell. The parallel is with a parallel glass structure, and on the glass substrate with spin coat ITO electrode, and on the ITO electrode with spin coat polyimide layer. Then we use cloth to buff the polyimide layer and induce the rubbing direction and pre-tilt angle. So we fill in the liquid crystal into the cell. Then the liquid crystal align along the rubbing direction. That's the basic series. So under this condition, strong ampere condition, the rise time is equal to this equation, and decay time is, you can see here, is proportional to viscoelastic constant in the cell gap square. So it's easy to understand low viscosity material have faster response time. And also from phase retardation, this equation you can see with a fixed retardation. For example, for liquid crystal display, we need 1 pi phase retardation. But for photonic application, you already need 2 pi application, 2 pi phase change. So with the high birefringence liquid crystal will enable a single cell gap. As cell gap response time is proportional to d squared. So that's why how we realize faster response time. High birefringence, low viscosity, large delta epsilon. This one is for the voltage, because the liquid crystal start to rotate after the threshold voltage. So this is elastic constant. This is dielectric anisotropy. So with high voltage, the rise time can be assisted, can be improved by applying voltage.
What is this cell gap? Sorry, your accent is a little hard to follow for me at the moment. Maybe you get used to it later.
Yes, you asked what is cell gap, right? Okay, this actually slide shows the same concept. How to measure the birefringence and viscoelastic constant. You see the liquid crystal cell looks like this. Usually it is 8 micrometer, around 10 micrometers the size. So it is glass substrate and spin coated with ITO electrode, and then polyimide layer. So the lab use lab that view system apply a 1 kHz electrical signal to the liquid crystal cell. So the top layer and bottom layer, you can apply a voltage here, right? So then illuminate a helium ion laser to detect the illuminance, the transmittance. So we scan the voltage, then we get the transmittance. The transmittance voltage curve is this equation. Says where delta over 2, and delta is phase change. So phase is proportional to barrier fringes and cell depth. So by measuring the transmittance voltage curve, we can get barrier fringes. And this setup, the polarizer orientation is at 45 degrees with the rubbing direction of the liquid crystal cell. In liquid crystal books, you can find this derivation. How to get this equation with this setup? Okay. So then we also measure its dynamic property. We measure the relaxation time at a controlled phase retardation. For example, we balance the voltage at 1 pi. Then we remove the voltage and get a relaxation curve and fit this exponential equation and get the top zero. So we get a Whisker elastic constant. Okay. Next, I will talk about the dual frequency liquid crystal. In this part, I will talk about low crossover frequency liquid crystals, and then the faster response time to show the DFLC devices. Here shows the dielectric anisotropic relaxation curve, relaxation with frequency curve. So for dual frequency liquid crystal, it is positive at low frequency and it's negative at high frequency, where the dielectric anisotropy equal to 0 is called crossover frequency. So you can see we can apply low frequency voltage. It rotates along the electric field direction. And we will apply high frequency voltage. It rotates perpendicular to the electric field direction. So both rise time and decay time can be assisted by voltage. That's its advantage. From material side, dual frequency liquid crystal contains two materials. One is negative delta epsilon LC. The negative delta epsilon LC, its dielectric relaxation occurs at very high frequency. So it almost keep constant at frequency less than 1 megahertz. In this material, we want to keep large negative delta epsilon at a high frequency region. Why? From this curve, you can see actually this is a linear add-up of negative liquid crystal and positive liquid crystal. For only positive liquid crystal, this dielectric relaxation will relax to 0. It cannot never be negative. But when we add the negative liquid crystal, the whole curve shifts down. So this value is decided by the negative liquid crystal. And so for positive delta epsilon LC, we usually use this structure with the ester group for dual frequency. It has dielectric relaxation occurs at kilohertz. So that's usable for our application. And here, this is about theory. It's about the dielectric anisotropy. What is dielectric anisotropy? For liquid crystal, it's a special thing is it has all the parameters, right? It's not crystal. You can define dielectric anisotropy. So Meyer and Meyer developed mean field theory and correlate this dipole moment. This is a liquid crystal molecule. It has positive charge and negative charge. So dipole moment you can understand it is charge times distance. So with this, under an electrical field, it can rotate along the electric field direction. So this theory correlate the macroscopic material, the molecular property with this macroscopic physical properties related by this other parameter. And this shows the method to measure the dielectric anisotropy. We use two cells. One is homogeneous. All the liquid crystals align parallel to the glass substrate. Then another one is homotropic. All the liquid crystals align perpendicular to the substrate. Okay. So by this equation, we can measure the internal parallel and internal perpendicular, and take a ratio. Then we get dielectric anisotropy. However, low frequency liquid crystal has a technical challenge, which is it has dielectric peaking effect when you apply voltage larger than, for example, 50 kilohertz. That dielectric peaking is very serious. It can melt. It melts all the liquid crystal, so not usable anymore. And also from these two equations, you can see the delta epsilon decreases as temperature increases, which is not good. And crossover frequency shift to high frequencies. For these reasons, it's very urgent to develop low crossover frequency liquid crystals. Then comes our liquid crystal material. From negative liquid crystal side, as we mentioned, we want to use the liquid crystal with a large negative delta crystal, which can increase the value at high frequency region. And also it's helpful to reduce the crossover frequency. And from this compound, we can see these are all very high birefringence liquid crystal. Why? Because it has a toluene structure. Toluene is comprised with phenol, triple bond, and phenol. So all the unsaturated pi electrons conjugated with each other and have a large birefringence. Then from positive liquid crystal, this is the difficult part because there are so many molecular structures. We want to find one which have a very low relaxation frequency. So we have this structure, single ester, double ester, and this one. This one looks bigger, and because it has one more phenol, right? So and then the study is about compare these molecular structures.
How does this birefringence is responsible for the faster response time?
Here, in the second part of my talk, we'll talk about how birefringence have birefringence to really faster response time. Here, actually, it contributes to the cell gap. You remember for example, we want to realize one pi phase change, and we have birefringence at 0.3. We can do a calculation. Do calculation. The wavelength is for Qiong and Qiong is 632 micrometer, and for this cell gap 8 micron. So for example, the birefringence of the liquid crystal 0.3. Then what phase change can we get? So it's like
pi by 2.
Huh?
Approximately pi by 2.
This is 2. This is 0.6. Okay, that's about 8 pi, right?
8 pi.
8 pi.
Yes.
Okay. 8 pi. So we don't need such thick cell gap. We need, for example, we need 2 pi. Then this cell gap is only 2 micron. 2 micron is the 2 pi, right?
You didn't need to go into all those calculations. I just wanted a physical picture of it. I mean, as I understand, birefringence is you can divide a single beam of light into two, right? Isn't that what birefringence is?
What? What's your question again?
I thought the birefringence is something which is a crystal or a material that can divide light into two beams and two portions.
No, birefringence is when you have two different refractive indices along different axes in the optical.
Okay, here you can see the liquid crystal molecular. It has this direction. Liquid crystal is rod-like structure, and here this direction is an ordinary refractive index, and this one is ordinary refractive index. The refractive index is decided by the first thing, the oscillation phase conjugation. You see the other final triple bond, it has pi electrons, and that pi electrons contribute to the polarizability. This one, because liquid crystal has Ne and NO, so it's a uniaxial media. That's why it has phase retardation. This is liquid crystal cell. You can illuminate the polarized light at 45 degrees, and that illuminated light, polarized light, divided by two directions. One is along this NO, another one is along Ne. So after passing this cells, these two beams has phase retardation, right? This start comes from here, phase retardation. The beam divided by two, and one passes the long axis of liquid crystal, another one passes through the short axis of liquid crystal. So it has phase retardation. Because all the liquid crystal align along the liquid crystal cell, right? You have a polyimide layer, you rub the polyimide layer, so it has a rubbing direction. Okay. I think here a good question. I mean, this is the most important thing. We actually, to develop faster response time, it just birefringence is most important. So this is previous work of the dual frequency liquid crystal. In 1980, Martin Sharp developed the dual frequency liquid crystal for the first time. Look at the structure. We can see for the positive liquid crystal, it's very bulky. It has 4 phenol rings, 2 ester, and its side chain is also very big. So it means it has a very high viscosity. Negative liquid crystal at that time, they don't have a high birefringence, so there are drawbacks. But they can realize the crossover frequency at 1 kilohertz. And now it's our work. From negative liquid crystal side, we change because this structure, the dark epsilon is -4, and this one is -8. The dielectric anisotropy of the DFLC is a linear add-up of -1 and +1. So with a larger value, dark epsilon will help the whole dielectric relation curve shift to negative region, and as it shifts, the crossover frequency decreases. So we substitute 10% this difluoro structure with two pairs of difluoro structure. We get the crossover frequency from 28 kilohertz to 18 kilohertz. Then we want to compare these two positive liquid crystals. We see the difference. One with 1 ester group, another one with 2 ester group. And we make 2 mixtures, and each of them has 15% positive liquid crystal, and with the same negative liquid crystal host. So we just want to compare this negative positive one. And we measure its dielectric constant. We can see this one. This one has a lower, three times lower dielectric relaxation frequency than the first one, and also it has a larger dielectric constant value. So from this picture. And this figure shows the dielectric anisotropy, the used one, because it's not particular, it keeps constant. It don't have dielectrical relaxation. So we can see the crossover frequency is also 3 times better, and also the dielectric constant is bigger.
How does the frequency affect the bifringence?
Oh, this is not related.
It's not related.
Yes. This dielectrical relaxation is a property of a small group of liquid crystal material. But even though most liquid crystal material has dielectrical relaxation, but it happens at megahertz, very high. Only some liquid crystal material with ester group or some group, the liquid crystal has dielectrical relaxation at kilohertz. But it's not related with birefringence. Birefringence is decided by this final ring. Actually, this ester group separates these 2 rings, and this birefringence of this big crystal is very small.
Let me get this right. I mean, in order to get a faster response, you're going to operate the liquid crystals in the high frequency range.
Yeah.
Right?
Yes.
My first question is then why do you need a dual frequency liquid crystal anyway? I mean, why would you need the low frequencies? If you want to get a faster response, you would just opt for the higher frequency region. And secondly, I mean, all right, let's go right with this person.
I think I understand your question. This is a factor affecting the response time. The dual frequency liquid crystal belongs to this category. Use voltage. You see this birefringence viscosity is related with material, but this also we can see a factor here, voltage. So for all the liquid crystals, we can get a faster rise time. But for dual frequency crystals, because we can use high frequency voltage driving, so for decay time factor, we can also have such a factor. So both rise time and decay time can be assisted by voltage. Next I will show you the structure for all other group members in our group. They did better work. They design this structure with 4 funnels and 1 ester group, and it can realize crossover frequency less than 1 kHz. It's a breakthrough. And also we found out this structure, which is the largest, the molecular structure with the largest birefringence so far. But somehow it can make a mixture with a dielectric crossover frequency at 28 kHz. So now, after introduce the experimental results, we want to think about what is dielectrical relaxation. You see this under electrical field. This is a liquid crystal molecule. We notice that these small arrows move much faster than the molecular structure itself. So that is called induced polarization, and it's time of around 10 to minus 12 seconds, so very fast. And this molecular movement is by orientation polarization. So it's a time scale is about 10 to minus 3, 10 to minus 2. So it's comparable to the electrical field switching rate. So when the electrical field switch very fast, for example 50 kilohertz, the liquid crystal molecule cannot follow the electrical field anymore. And so it has dielectrical relaxation. The bi-relaxation equation assumes for this dielectrical relaxation only have one dielectric frequency. So this is a dielectrical relaxation type. And further, we know the orientation from the liquid crystal material, the orientational order of the nematic liquid crystal. As I mentioned just now, the orientation polarization is actually because the nematic potential. The liquid crystal material the interaction, right? From isotropic phase become nematic phase. The liquid crystal gradually form the direction. So that the force between moleculars is called nematic potential. And that potential hinders the rotation of the molecules around the short axis. This is the molecular, it rotates around the short axis. So this is called retardation factor. And also in this book, they set up a model. You can look at the liquid crystal as a sphere, and it's suspended in an isotropic media with viscosity eta. And this it shows the relaxation time of the liquid crystal molecule is proportional to related to its size. So in conclusion, we think the large molecular size and large nematic potential leads to low relaxation frequency. Okay. Now this slide shows the deep field frequency operation mechanism. As we said before, both rise time and decay time can be assisted by the voltage. So you can see this is just the liquid crystal cell switching. When you apply voltage, this shows two results. One example is use low crossover frequency material and work at 45 degrees. When you increase temperature 10 degrees, the viscosity drops 2 times. So at high temperature, it has low viscosity, and that is realized 634 microseconds response time. And I use this EFLCU in the polymer dispersed system, and I fix the voltage at 75 volt, and it's just scan the frequency 1 kilohertz, 30 kilohertz, and get this 2 milliseconds and 0.5 milliseconds. Okay, now I'm going to talk about what?
Yes, I just want to remind myself, how are you measuring the time, the rise time of the quantum? The response.
Okay. Actually, in the lab, we use the oscilloscope.
Okay.
Yeah. That function is called catch the this is just a move in oscilloscope. You can catch the whole curve. When you remove the voltage, the transmitter voltage curve relax, right? And it can catch this free of the response time. Okay, next we will going to talk about high birefringence, negative dirty inflow phenolphthalein, cyclohexane structure. And in this part, first I will introduce the electro-optical properties, and then use RV refractometer to measure its birefringence. It was reported by these publications the toluene structure, phenolphthalein structure, has very high birefringence. We measure its absorption spectrum. There are two peaks. One is at about 200 nanometers, and this is induced by delta bond in the molecular structure. And this one is about 300 nanometers because of resonance wavelengths. And this one, the longer resonance wavelengths, the larger birefringence. So we have two groups of molecules. This one is cyclohexane toluene structure, and this one is phenolphthalein structure. So this one has larger birefringence than this one. We can see this all in the same group. The main part is the same. Only difference is on the side chain. So it's called homologs. And we want to measure its property property and compare the difference between these homologues. But all the materials have very high melting point, so it's difficult to measure it directly. So we choose guest host method. We choose a host. It is either commercialized liquid crystal or mixture. You know all the properties you have already known. So usually we choose a host mixture at which the liquid crystal, this gas compound has good solubility, and also the host structure, the host mixture should have similar physical properties. For example, if we want to extrapolate the birefringence, it has similar birefringence as the gas compound, the two principles. So we choose this one called -1. It has a very low melting point, which is good for the solubility. And this birefringence, and this is dark ethanol. Because this dark ethanol for this molecular structure is about -4 to -6. So this one is -5.1. Then this is the result. I do 10% each of them into the -1 host and measure its birefringence at different temperatures and feed by this equation. This equation tells us the birefringence decreases as temperature increases. And the improvement for phenolphthalein is 17%, for the cyclohexane is 13%. And now this equation shows the viscoelastic constant, the temperature dependent. Let's say it's related with activation energy and other parameter. So as temperature increases, this because of this it decreases. Then as temperature goes to clearing part, this one goes to 0. So the viscoelastic constant increases a little bit. So we can see even all the homologues has the difference is only on the side chain, but the viscosity has big difference. So we have the conclusion: the longer the altitude, the larger the viscoelastic coefficient. This one, figure of merit, actually is a combination of birefringence and the viscoelastic constant. So because the birefringence doesn't change very much, the figure of merit is decided by the viscoelastic constant. So for this one, the largest one is 504, and this one is 302.
The figure of merit arbitrary. Why does it have a birefringence square and why?
This birefringence square divided by viscoelastic constant.
Why? Why is it the square? Is it arbitrary? Is the definition of figure of merit arbitrary or?
No, it's the represent response time. Also very good question. I spent a lot of time to understand. You can see the response time is this equation, right? This one. And phase change is so. For example, phase retardation is fixed, and what is d square? D square should be delta lambda divided by 2 pi, the birefringence. So we actually substitute this to this and get the figure of merit. Figure of merit is equal to 1/tau 0. 1/tau 0. We are going to cancel the cell gap. Okay. So this is figure of merit. So to measure the birefringence more accurately, we find there's always inconsistent when use electro-optical method. So to measure the birefringence, we use the RB refractometer. This shows the principle. So this is the prism. This is the crystal material. By changing photo-internal reflection stage. And so then we can see a very clear edge. At this moment, we read the data, and this is the refractive index. So this is NE, and this is NO. The average refractometer can be accurate as 0.0001. So this is the intraoptic data. For the guest host system, we know the birefringence of host, and we measure the birefringence guest host. We do 10% into the host. So then we can interpolate this guest birefringence of guest. So we get this data. For this group of liquid crystals, the birefringence from 0.38 to 0.34, and for cyclohexane toluene, it was 0.29 to 0.26. And actually, in the real measurement, there is always inconsistent. Later we find the solubility of this compound in the -1 is not good because it precipitated after one night. So we change it to another host, and found its solubility is good and get good properties data. Now I'm going to talk about spot diluter effect on the negative liquid crystals. Actually, this slide is for liquid crystal display. In liquid crystal display, slow response time can induce the image blurring. And also in color sequential display, the slow response time can induce color breakup. So it's also very important to develop liquid crystal response time less than 1 millisecond. But there are two ways to do this. Firstly, we can synthesize molecular structure and get faster response time. Another way is we can choose a group host. Then we dope small molecules to modulate its liquid crystal property. So here we choose binary. This is a tophenyl structure, and it's difluorotophenyl structure. It has a birefringence 0.23. For liquid crystal display application, this is a large value. For photonic display, the birefringence is about 0.3 or even 0.6. But for display, usually the birefringence is very low, 0.06 or something. So this is very large value. And also this material, it has low viscosity. And because of the supercooling effect at room temperature, this binary host is liquid crystal phase. I don't know if you understand supercooling effect. Okay. Because this usually the liquid crystal mixture, liquid crystal single compound is a crystal powder. In order to make a liquid crystal mixture, we usually make 10 or 12 compounds together. It is called eutectic mixture. So it is liquid crystal phase. But here we only use two single compounds. So usually it's difficult to get liquid crystal phase at room temperature. Only use two compounds. So this two compound is very good. And we dope diluters. For example, this one, cyclohexane, it has two effects. First, it improves the vertical alignment of a negative liquid crystal. And secondly, because the small diluters can reduce the liquid crystal system, the clearing point of the system. So it actually modulates every parameters. We will introduce this later. This is a previous work. They dope this 5CD, this liquid crystal single compound, and improve the dark state. This figure shows the transmittance voltage curve, a typical transmittance voltage curve of a liquid crystal cell. Here we call it dark state. You see, under cross the polarizer, the liquid crystal cell is totally dark. But for bad alignment, it looks like this. Okay. So we actually this one is our host, the final structure. At room temperature, it is good, but at 75 degrees C, you see dark state become smeared and not good. So we go to 10% of the bicyclohexane, and the lemon improved very much. You see very briefly the dark state. And this is also mechanism. Why it has a lemon problem? Because the substrate with surface energy lower than the LC surface tension cause homotropic lemon. Otherwise, a lemon is parallel to the substrate plane following any long range order. So diluter actually change the LC surface tension and improve its alignment. The systematic study of diluters effect on the liquid crystal display has not done before. So this work we choose 6 diluters and study its effect. So this table we also again use gas host method to measure first its clearance part, secondly is birefringence. So it can be a reference for other people to use. So which one I want to use to make a liquid crystal mixture. So this is the birefringence and this is the clearance part. We found for some liquid crystal diluters, it's extrapolating value and is very close to the directly measured value. That means this diluter has a deep crystal phase. But for some other liquid crystals, for example, this one difference is very big because this structure does not have deep crystal phase. So I measured the clearance part, and by doping 5%, 10%, 20%, and 30% for 6 diluters, and see how the clearance part change. We can see it decreases linearly, and also you can see for this diluter the clearance part drops 18 degrees. Which is good because for high clearance part, that means the liquid crystal device at room temperature is less sensitive to the environment. So it's important to have a high clearance part. This figure shows the birefringence. So again, I measure the host first, then I measure the 5%, 10%, 20%, 30%, and measure the birefringence. This is host property. And you see, you check this tendency. It's almost linear. So, and in this category, this one is the biggest one. It can be static because this is the final structure, so it has the largest birefringence. This one is a diluter effect on viscoelastic constant. So we also compare again. Please pay attention to the trend. Okay. We found that the viscoelastic constant drops, but somehow try to saturate at some concentration. And another one is this one is the best. It has the lowest viscoelastic constant. And so this bigger variable is actually a combination of birefringence and viscoelastic constant. We also see the trend. Here we can see the final structure is the best. This one is the best. But we remember this one has a very bad performance on the clearing part. But clearing part is very important. So this one actually have a secondary best performance. So we choose this dicyclohexane to have a further study on temperature effect. This is measurement. This black line is the host. So 5%, 10%, 20%, 30%. We can see the birefringence change almost linearly with concentration increases. We measure experimentally and feed with the equation. And this one is viscous elastic constant. We can see 20% and 30% almost overlap with each other. So, so this tells us one thing: it doesn't at a certain percentage, the viscosity doesn't increase anymore. So we should not dope more than that. So keep like 20%. So this is the viscous elastic figure from Marriott. Consider both the birefringence and the viscous elastic constant. We can see at room temperature of this region, 25 to 55 degrees, the blue line is largest, so 20%. And at high temperature, like from 55 degrees to 95 degrees, this red line is less, so 10% is less. Okay, so this work actually is a study of a dilutory effect on the liquid mixture. In the industry, they load a lot of diluters into the mixture to modulate its properties. So it's a study which one to use okay. Lastly, is a summary.
Just one question. In the diluted effect, so you made some experimental observations. So it seems that somewhere between 10 and 20% you will get the optimal figure of matter.
10 to 20?
Yeah. 10% seems to be highest, 20% going down, 30% going up further. So maybe between 10 and 20% somewhere would be the maximum, the peak figure of matter to be probably getting, right?
You mean this one is
10%?
this which one? 35 is much worse.
Yeah.
20, this is 10.
Yeah.
5 is here.
Yeah. So between 10 and 20 somewhere,
Mm-hmm.
you would expect sort of, the best figure of matter?
I think so. Yes.
So have you sort of modeled this aspect as well? This is observation, right? So in terms of the diluted effect and how it would impact the figure of matter, or just observation?
You mean what do you mean observation? We measure each data.
Yes.
Yeah.
So you measure it probably because the exact effect of the diluted was not known. So you try different concentrations to see the impact.
Yes.
Right?
Yeah.
So with these observations, were you able to sort of draw some conclusions in general or modeling it or somehow?
But without modeling.
Without
modeling. Yeah. Yes.
But is there some theory sort of to model it as well or just observations right now?
I think it's observation because the liquid molecules modeling, I think it will be very difficult. Our group modeling is only focused on a single molecule. To model a single molecule, for example, dipole moment related with the electric constant or the polarizability with the birefringence. Okay. Finally, this is a summary. First part of my work is trying to develop low crossover frequency compounds. Experimental results shows double ester compound has 3 times lower dielectric relaxation frequency and larger dielectric anisotropy than a single ester. And the sub-millisecond DFRC device has been made. Secondly, 4-difluorophenolcholine and cyclohexylcholine were evaluated on their birefringence, viscoelastic coefficient, and figure of marriage. Birefringence varies very little between polynomials, but viscoelastic coefficient increases as alkyl chain size increases. The application of a high birefringence phenolcholine for infrared application is foreseeable. Thirdly, the diluters is widely used in LC application. We have studied systematically the effects of 6 diluters for lowering the viscosity while stabilizing the vertical alignment of the final host mixture at elevated temperature. The pros and cons which diluter are analyzed. Okay, thank you. And finally, I'm going to show some pictures. Where is this? This is Shanghai bomb. This one is Zhangjiao Taitai. Right now, it has a lot of companies in pharmacy and in electronics. So I'm going to work at work So Merck is famous for its pharmacy, but actually it's also the largest liquid crystal material company in the world. They will start a research and development lab. And first, at the beginning, just cover the customer service or support. Later, we'll cover the full spectrum of LC R&D activities, including mixture development and defect analysis. Welcome you to Shanghai. Visit Shanghai. Okay, thank you.
There are any questions we had about already, but there are some more.
Nanjing High-Tech Research Park is around China?
Yes, it is on the eastern Pudong region. It is on the east part of Pudong.
Can you tell us something about the rare earth metal production in China?
Manufacturing production?
Rare earth metals.
What?
Rare earth metals. It's not really the presentation, I'm just asking that.
Rare earth metal production in China.
If you
I've heard a lot about it.
idea about it.
What metal?
Rare earth.
Rare earth metal.
Rare earth metal. I read the news. It's in Mongolia, in inner Mongolia, at Urduz.
How big is the facility?
Huh?
How big is that facility?
How big? I have no idea, to be honest. But I heard that China has a lot of rare earth metal. they are rich people. We are not. We not belong to that.
So they're not rare anymore.
There are no more questions. Let's thank you. So Dr. Qiong is going to be here today